dark energy is one of the most mysterious and elusive forces in the universe. Inferred from observations of the accelerating expansion of the cosmos, dark energy is believed to make up about 68% of the universe. This vast, unseen energy is a crucial piece of the puzzle when it comes to understanding the cosmos, as it plays a key role in driving the accelerating expansion of the universe. But could it be a literal power source, in the way we think of energy like electricity or fusion? Given the nature of dark energy, harnessing it presents enormous challenges that we have yet to fully understand, particularly due to its diffuse nature and our lack of understanding of its fundamental properties. Could we ever find a way to harness it to drive technological advancements or even sustain an entire civilization? While it's tempting to imagine harnessing dark energy to power our technology or even future space civilizations, the reality is more complex and challenging than we can currently comprehend. Dark energy is thought to be a property of space itself, an intrinsic force that pushes the universe apart, driving its accelerating expansion. To visualize this, imagine space as an elastic fabric that is constantly stretching, with dark energy acting as the force that pulls the fabric in all directions, making the universe grow larger over time. This expansion operates over vast cosmic scales, making dark energy fundamentally different from other forms of energy that can be easily captured and utilized. It's not like the energy we get from the sun or from nuclear fusion, which we can capture, convert, and utilize directly. Instead, dark energy is diffuse and spread across the entirety of space, making it exceedingly difficult to even conceptualize how we might harness it. Moreover, dark energy is incredibly weak on a local level. Its influence is only felt across the vast, empty stretches of the universe, meaning any attempt to use it would require technology capable of manipulating the fabric of space-time itself, something far beyond our current capabilities and understanding. The fundamental nature of dark energy remains an enigma, and any technology that could make use of it would have to operate on principles we have yet to discover. It would involve reshaping our understanding of the laws of physics and developing technologies that can operate at an unimaginable scale. However, if a Type 3 civilization on the Kardashev scale, one capable of harnessing the energy of an entire galaxy, could somehow figure out how to tap into this energy, it could potentially open doors to unimaginable technologies. Such a civilization might use dark energy to manipulate the expansion of the universe or even stabilize regions of space-time to create habitable zones or prevent cosmic disasters. For example, they could stabilize space-time to create safe zones for planets, ensuring that these regions remain conducive to sustaining life. They could also use dark energy to counteract gravitational collapse in certain regions, effectively creating a bubble of stable space-time that could support life. Alternatively, they might harness dark energy to control the rate of universal expansion in specific areas, allowing for the formation of new stars and planets where conditions are ideal for sustaining advanced civilizations. Maybe this energy could even be used to power intergalactic travel or create artificial wormholes. The implications of being able to harness dark energy would be profound, offering possibilities that currently exist only in the realm of science fiction. But for now, dark energy remains more of a cosmic force than a power source we can access, tantalizing us with its possibilities while remaining firmly out of reach. The mystery of dark energy continues to challenge our understanding of physics and cosmology, largely because it drives the accelerating expansion of the universe and remains fundamentally unexplained. It reminds us that the universe still holds secrets far beyond our grasp. Dark energy speaks to the limits of our knowledge and the vast potential of what we have yet to learn. Could we ever learn to wield such power? It's a question that drives both scientific curiosity and our imagination for the future. As we continue to explore the cosmos, dark energy stands as a reminder of the profound unknowns that await us. It serves as a beacon for future generations of scientists and dreamers, pushing us to question, explore, and reach beyond the limits of our current understanding. Current research efforts, such as studying the effects of dark energy on cosmic structures and refining our cosmological models, reflect our commitment to unraveling this mystery, reminding us that the journey of discovery is ongoing and full of promise. If you enjoyed this exploration into the mysteries of dark energy, be sure to like, share, and subscribe to this channel for more fascinating insights into the universe. Together, let's keep reaching for the stars.
Harnessing a black hole as a gateway to the stars could be the key to future space travel. A concept that might seem like pure science fiction but has intrigued scientists and dreamers alike. The idea of using black holes for space travel has captivated researchers for decades, and while it remains speculative, current physics offers some tantalizing glimpses into how this might be possible someday, sparking the imagination of researchers and enthusiasts worldwide. One theory suggests that black holes could be used as gravitational slingshots. The immense gravity of a rotating black hole, especially one known as a Kerr black hole, could theoretically be used to whip spacecraft around at incredible speeds. This could potentially allow us to explore vast distances in a fraction of the time it would otherwise take. This is thanks to an effect called frame dragging, where the black hole's spin warps spacetime around it, creating a kind of cosmic boost for anything orbiting close enough. But not too close, unless you want to be stretched into spaghetti by tidal forces. The concept of using gravitational slingshots isn't new. Space agencies already use planetary gravity to accelerate probes, but employing a black hole takes this idea to a whole new level of power and complexity. Another, even more speculative idea is using the concept of white holes, theoretical opposites of black holes that expel matter rather than sucking it in. If we could find a way to connect black holes and white holes through hypothetical wormholes, we might have a natural cosmic highway that could allow for nearly instant travel between distant parts of the universe. However, this concept is entirely speculative and remains highly theoretical, with no current evidence supporting its feasibility. Such a wormhole, often called an Einstein-Rosen bridge, is a theoretical tunnel that could link two points in spacetime, making it possible to traverse unimaginable distances almost instantaneously. However, maintaining such a wormhole stable enough to travel through, and without collapsing into a black hole itself, remains purely theoretical and far beyond our current technological capabilities. The energy requirements, not to mention the exotic matter needed to keep a wormhole open, are hurdles that we have yet to understand, let alone overcome. There are also ideas related to harvesting energy from black holes, which could be crucial for making interstellar travel possible. One such concept is the Penrose process, which involves extracting energy from the ergosphere of a rotating black hole. The ergosphere is the region just outside the event horizon where spacetime is dragged along by the black hole's rotation. By sending matter into this region and carefully managing its trajectory, it might be possible to extract significant amounts of energy that could theoretically be used to power a spacecraft or sustain a long-term mission. Another related concept is Hawking radiation, a theoretical form of radiation that black holes might emit due to quantum effects near the event horizon. This radiation is significant because it suggests that black holes are not entirely black but can lose mass over time, potentially evaporating completely. Harnessing Hawking radiation could provide a unique and powerful energy source for advanced space missions. Although we haven't observed it directly yet, if harnessed, it could provide another potential energy source. Black holes also present the fascinating concept of time dilation, which could have implications for future space travelers. For example, time dilation has been observed in practice with GPS satellites, which need to account for both the effects of Earth's gravity and their high speed to maintain accurate timekeeping. According to Einstein's theory of general relativity, time moves more slowly in areas of intense gravity. This means that if a spaceship could safely orbit close to the event horizon of a black hole, time would pass differently for those on board compared to people far from the black hole. In theory, this could allow for a form of time travel into the future, where astronauts could experience only a few years while decades pass elsewhere in the universe. This concept, while incredibly intriguing, presents enormous challenges, including the difficulty of getting close enough without being destroyed by tidal forces and the need for advanced propulsion systems to escape the gravitational pull. For now, using black holes for space travel is still in the realm of science fiction. But the ongoing study of black holes, including projects like the Event Horizon Telescope, continues to push the boundaries of our understanding. These endeavors are not just about taking pretty pictures of black holes. They have led to specific discoveries, such as capturing the first image of a black hole's event horizon. This achievement is significant because it confirms the existence of event horizons, helps validate Einstein's theory of general relativity, and provides critical insights into the behavior of matter and energy in extreme gravitational fields. These efforts are crucial steps in deciphering the complex nature of spacetime, gravity, and the universe itself. Perhaps one day, the mystery of black holes will hold the key to humanity's journey among the stars, turning science fiction into a remarkable reality. Until then, we continue to learn, hypothesize, and dream, inching ever closer to understanding these enigmatic objects that may one day become the stepping stones for interstellar exploration. If you enjoyed this exploration into the possibilities of black hole space travel, don't forget to like, share, and subscribe for more deep dives into the cosmos and beyond.
Imagine a planet floating alone in the dark, far from any star, an interstellar wanderer known as a rogue planet. It may seem like a cold, lifeless rock drifting through the endless void, but could dark matter actually hold the key to supporting life in these bleak environments? Rogue planets are estimated to be surprisingly common in our galaxy. Without a parent star, they lack the steady sunlight we associate with life, and temperatures can plummet to extremes. However, scientists have hypothesized that under certain conditions, life could still exist. Perhaps deep underground, where geothermal heat or even interactions with dark matter could provide the necessary energy. These hidden environments could harbor subsurface oceans or pockets of liquid water, potentially offering a stable environment for microorganisms to thrive despite the harsh conditions on the surface. Dark matter makes up roughly 85% of the universe's mass. It is elusive, mysterious, and doesn't emit or absorb light. Yet some theories propose that dark matter particles could interact with regular matter in ways that generate heat, which is particularly relevant for rogue planets that lack other energy sources. If rogue planets were to move through regions of space dense in dark matter, these interactions might produce enough heat to maintain subsurface oceans or even support biological processes. This process is similar to how tidal forces from Jupiter's gravity keep Europa's ocean warm. This constant source of energy could be crucial for maintaining a habitable environment, even in the absence of a nearby star. Could this mean rogue planets have the perfect conditions for life, albeit not the kind we usually imagine? Unlike Earth, where sunlight drives most ecosystems, life on rogue planets might rely entirely on geothermal energy or dark matter interactions, creating an entirely different set of biological processes. If a rogue planet had a thick atmosphere, geothermal heat, or enough gravitational compression, it could support a stable temperature. Adding dark matter to the mix could help maintain these temperatures for longer periods by providing an independent source of heat. The interactions between dark matter and regular matter could create a surprising amount of warmth, allowing liquid water to exist and potentially providing the energy needed for basic metabolic processes. What makes this idea so fascinating is that rogue planets could be anywhere, and many may be much closer to us than even the nearest star. These planets, free from the gravitational bonds of a parent star, could drift through the galaxy, and some could even pass relatively close to our solar system. If dark matter is playing a role, the galaxy could be full of habitable worlds that we've barely begun to understand. The sheer number of rogue planets is astounding. Combined with the possibility of dark matter interactions, this suggests the possibility of countless hidden environments where life could take hold. It's hard to say this environment would be so different from our own. But extremophils, organisms that thrive in the most extreme conditions on Earth, hint that life can adapt in ways we never thought possible. On Earth, extremophils have been found thriving in places with intense pressure, extreme heat, or complete darkness, such as hydrothermal vents on the ocean floor. The prospect of life tapping into dark matter as an energy source pushes our understanding of biology and the conditions under which life can arise. Life on rogue planets might have developed unique adaptations to utilize the energy provided by geothermal heat and dark matter interactions, leading to completely new biological processes that are unlike anything we've seen on Earth. The concept of dark matter heating rogue planets might seem speculative, but it's these kinds of what-if questions that expand our horizons. Throughout history, speculative questions have often led to significant scientific discoveries, reminding us of the value of exploring the unknown. After all, rogue planets are thought to outnumber stars in our galaxy, which raises an incredible possibility. Maybe the universe is teeming with more life than we ever imagined, hidden not around shining stars, but drifting in the dark. Imagine a galaxy where rogue planets, each with its own unique conditions, harbor microbial life or even more complex ecosystems, evolving in isolation without the need for sunlight. Such a possibility changes our perspective on what is necessary for life to exist and reminds us that the universe is full of surprises, waiting to be discovered. The study of rogue planets and the role that dark matter might play in heating them is still in its early stages, but it provides an exciting avenue for future exploration. Current and upcoming missions, such as the James Webb Space Telescope and potential next-generation space probes, could help us gather more data on these mysterious planets and detect signs of subsurface activity. As our understanding of dark matter improves, and as technology advances, we may be able to detect these elusive planets and probe their environments more closely. Perhaps one day we will find evidence that even in the darkest corners of space, life can find a way to survive and thrive, proving once again that life is more resilient and adaptable than we could ever imagine. If you enjoyed this deep dive into rogue planets and the mysteries of dark matter, don't forget to like, share, and subscribe for more explorations into the universe's hidden secrets. Antimatter and dark matter, two of the universe's most enigmatic phenomena, shrouded in mystery but critical to our understanding of the cosmos. While they sound similar, their properties and roles couldn't be more different. Let's explore what sets them apart, why they matter, and how they might shape the future of space exploration and physics. Antimatter, the mirror opposite. Imagine a mirror image of everything you know, a world where particles have the same mass but opposite charges. That's the realm of antimatter. For every particle of matter, there exists an equivalent antiparticle. Protons have antiprotons, electrons have positrons. When antimatter comes into contact with regular matter, the result is spectacular: mutual annihilation. This annihilation process releases an enormous amount of energy, making antimatter one of the most efficient energy sources imaginable. But there's a catch. Antimatter is extraordinarily rare. It's produced naturally in minuscule amounts during high-energy processes like cosmic ray collisions and in particle accelerators like those at CERN. Even so, creating just a single gram of antimatter requires staggering amounts of energy and resources. And then there's the storage problem. Since antimatter annihilates on contact with matter, it must be suspended in a vacuum using magnetic fields, an incredibly delicate and challenging process. Despite these hurdles, the potential is enormous. Imagine spacecraft powered by antimatter propulsion, capable of reaching speeds close to the speed of light. It could revolutionize space travel, turning interstellar missions into a feasible reality within a human lifetime. Antimatter, with its promise of efficiency and power, holds the key to solving some of humanity's greatest challenges in energy and exploration. Dark matter, the hidden glue of the cosmos. Now let's turn to dark matter. Unlike antimatter, dark matter doesn't annihilate, emit, or reflect light. It's completely invisible, detectable only through its gravitational effects on visible matter. Scientists estimate that dark matter makes up about 27% of the universe's mass energy content. Without it, galaxies as we know them couldn't exist. The stars and gas within galaxies move too fast for their observed mass to hold them together. Dark matter acts as a gravitational glue, providing the missing mass needed for their stability. But what is dark matter? That's the mystery. It might be made of exotic particles like WIMPs, weakly interacting massive particles, or axions, but we don't yet know for sure. And while it doesn't have immediate practical applications like antimatter, Its importance to understanding the universe is profound. Dark matter shapes the large-scale structure of the cosmos, influencing how galaxies form and evolve. Without it, the universe would look vastly different. How are they different? The differences between antimatter and dark matter are striking. Antimatter is a known counterpart to regular matter, capable of producing immense energy through annihilation. Dark matter, on the other hand, is invisible and interacts primarily through gravity, acting as the framework on which galaxies and cosmic structures are built. Antimatter holds promise for practical uses, particularly in energy and propulsion systems. Dark matter is a cornerstone of theoretical physics, helping scientists understand the fundamental nature of the universe. While antimatter can be studied directly in laboratories, dark matter remains elusive, studied indirectly through gravitational lensing and the motion of stars and galaxies. These differences highlight the complexity of the universe and the distinct roles these phenomena play in shaping it. The role of antimatter in space exploration. Antimatter propulsion could be the key to interstellar travel. With an energy density millions of times greater than that of chemical fuels, antimatter could power spacecraft to unprecedented speeds. Such technology might one day allow us to explore distant star systems, transforming science fiction into reality. But before we get there, significant challenges remain. The cost and difficulty of producing and storing antimatter must be overcome. Even with current advancements, we are far from the efficiency needed to make antimatter propulsion a practical option. Still, the potential is too great to ignore. Antimatter represents a future where humanity can truly become an interstellar species. Dark matter and the secrets of the universe. While dark matter doesn't offer immediate technological benefits, its role in understanding the cosmos is unparalleled. Without dark matter, galaxies couldn't have formed, and the universe's structure would be unrecognizable. Dark matter also influences gravitational lensing, bending light from distant stars and galaxies, helping scientists map the unseen. And it raises profound questions. Does dark matter consist of new, undiscovered particles? Could it point to extensions of the standard model of particle physics? Is our understanding of gravity itself incomplete? Answering these questions could unlock new frontiers in cosmology and physics, reshaping our understanding of reality. Why do these differences matter? The significance of antimatter and dark matter lies not just in their unique properties, but in their broader implications. Antimatter offers a glimpse into the future of energy and propulsion, potentially solving critical challenges in space travel and energy sustainability. Dark matter, by contrast, holds the key to unlocking the universe's hidden structure, answering fundamental questions about the nature of existence. Both are essential for advancing our understanding of the cosmos. While one might power our spacecraft, the other helps us understand the galaxies we aim to explore. The future of exploration and discovery. As scientists continue to study antimatter and dark matter, the possibilities are endless. Could we one day harness antimatter to explore distant stars? Could understanding dark matter reveal new physics that redefine our place in the universe? These questions drive the pursuit of knowledge, inspiring future generations to explore the unknown. Antimatter and dark matter might be mysterious, but together they reveal the complexity and wonder of the cosmos. They remind us that there is still so much to discover, and that the universe's greatest secrets are often hidden in plain sight. What do you think? What excites you more, the potential of antimatter or the mystery of dark matter? Share your thoughts in the comments, and don't forget to subscribe for more cosmic explorations. Until next time, stay curious and keep reaching for the stars. The Alcubierre Warp Drive, science fiction's most tantalizing dream or humanity's future reality. Imagine traveling to distant stars and galaxies faster than the speed of light. Warp drives, popularized by Star Trek and other sci-fi, suggest a way to overcome the universe's ultimate speed limit. But could this idea ever leave the realm of fiction and become reality? Let's dive into the fascinating world of the Alcubierre warp drive to see if faster-than-light travel is more than just a fantasy. What is the Alcubierre warp drive? In 1994, physicist Miguel Alcubierre proposed a groundbreaking idea. What if we could achieve faster-than-light travel without breaking Einstein's theory of relativity? Rather than accelerating a spacecraft beyond the speed of light, the Alcubierre warp drive bends space-time itself. By expanding space-time behind a spacecraft and contracting it in front, a warp bubble could theoretically carry the craft faster than light, without it moving through space in the traditional sense. Inside this bubble, space-time remains flat and stable, keeping the ship and its passengers safe. It's a radical concept, but how could it actually work? How could it work? The key lies in Einstein's theory of general relativity, which tells us that space-time can be warped by mass and energy. Imagine space-time as a flexible fabric that can be stretched, bent, or compressed. The warp drive would manipulate this fabric, creating a bubble of space-time that moves faster than light relative to the space around it. Here's a helpful analogy. Picture an ant walking across a sheet of paper. Normally, the ant would have to walk the entire distance. But if you bend the paper so the two ends touch, the ant can reach its destination much faster. In a similar way, the warp drive would fold space-time, bringing distant points closer together. The role of exotic matter. While this sounds exciting, there's a catch: exotic matter. To create and maintain a warp bubble, you'd need a form of matter with negative energy density. This exotic matter could counteract the immense gravitational forces that would otherwise collapse the warp bubble. But here's the problem. Exotic matter is purely theoretical. Some speculate that dark energy, the mysterious force accelerating the universe's expansion, could play a role. Unfortunately, our understanding of dark energy is still in its infancy, and producing or controlling exotic matter is far beyond current technology. Without it, the warp drive remains just a fascinating idea. Energy requirements, the cosmic power problem. Even if we could harness exotic matter, there's another hurdle: energy. Early estimates suggested that creating a warp bubble would require energy equivalent to the mass of a star. Recent refinements have reduced this requirement, but it's still astronomically high. For now, the energy demands make the Alcubierre warp drive impractical. But what if future discoveries in quantum physics or energy manipulation unlock new possibilities? The dream of faster-than-light travel keeps pushing scientists to explore the limits of what's possible. Causality and time travel, a cosmic paradox. Warp drives also challenge our understanding of time and causality. If faster-than-light travel is possible, could it lead to paradoxes where a spacecraft arrives before it departs? These causality violations raise deep questions about the nature of time and space. Physicists are still debating how, or if, these paradoxes could be resolved. But one thing is clear: the implications of warp travel go far beyond just getting from one point to another. Current research and possibilities. While the Alcubierre warp drive remains theoretical, it has sparked real-world research. At NASA's EagleWorks laboratories, scientists have been studying warp fields and exploring whether small-scale effects could mimic aspects of a warp drive. Though we are light years away from achieving practical warp technology, these experiments help us understand the underlying physics. Step by step, humanity is inching closer to turning sci-fi dreams into scientific breakthroughs. The future of faster-than-light travel. The Alcubierre warp drive represents one of the boldest ideas in modern physics. By bending space-time itself, it offers a vision of interstellar travel that could one day take us to the stars. But the challenges are immense, from the need for exotic matter to the staggering energy demands. For now, the warp drive is a symbol of human ingenuity and curiosity. It pushes us to ask questions, explore the unknown, and imagine a future where the impossible becomes reality. What's next? Could we one day build a warp drive and travel to distant galaxies? The answer remains uncertain, but the pursuit of such possibilities continues to inspire scientists, engineers, and dreamers alike. What do you think? Is faster-than-light travel humanity's next great frontier, or will it remain the stuff of science fiction? Share your thoughts in the comments below, and don't forget to subscribe for more explorations into the mysteries of the universe. Until next time, stay curious and keep looking to the stars. Time travel, the ultimate mystery. It's inspired countless stories, from H.G. Wells' The Time Machine to the mind-bending paradoxes of Back to the Future. But what if time travel isn't just a work of fiction? Could the secret to bending time lie hidden in one of the universe's greatest enigmas, dark matter? Today, we'll explore how this elusive substance could hold the answers to time travel and challenge our understanding of physics, space-time, and reality itself. The elusive nature of dark matter. To understand how dark matter could influence time travel, we need to unravel what dark matter is. Dark matter makes up about 85% of the universe's total mass. But it doesn't emit, absorb, or reflect light, which means it's invisible to even our most sophisticated telescopes. Its presence can only be inferred through its gravitational effects, like the way it holds galaxies together, or bends light from distant stars in a phenomenon called gravitational lensing. Scientists believe dark matter interacts with ordinary matter through gravity and potentially other unknown forces. But its exact composition remains one of the biggest mysteries in modern science. Some theories suggest it's made of exotic particles, unlike anything we've ever encountered. Others propose it might exist in massive undiscovered fields or clumps. Its mysterious nature raises an intriguing possibility. Could dark matter interact with space-time in ways that allow for time travel? How gravity and time are intertwined. Let's take a step back to understand how dark matter might influence time. According to Einstein's theory of general relativity, space and time are not separate entities. They're interwoven into a single fabric called space-time. Massive objects like stars and black holes create dents in this fabric. This distortion of space-time doesn't just affect the path of objects, it also slows down the flow of time. This phenomenon, called gravitational time dilation, means that time passes more slowly in stronger gravitational fields. For example, astronauts on the International Space Station age slightly slower than people on Earth due to the weaker gravitational pull in space. Now imagine if we could amplify this effect. If dark matter has significant gravitational properties, could it create distortions in space-time powerful enough to bend or even reverse the flow of time? The wormhole connection. One of the most exciting theories is that dark matter could help stabilize wormholes. Wormholes are hypothetical tunnels through space-time, connecting two distant points. Picture space-time as a sheet of paper with two dots drawn far apart. If you fold the paper so the dots touch, a wormhole would act as a tunnel connecting them, allowing for instantaneous travel. But wormholes aren't just about moving through space. They could also connect different points in time. The problem? Wormholes are incredibly unstable. They would collapse almost instantly without an external force to hold them open. This is where dark matter could come in. With its gravitational properties, or perhaps some yet-to-be-discovered interaction with space-time, dark matter might provide the stability needed to create traversable wormholes. Could dark matter be the missing ingredient in creating stable, usable time portals? Dark matter and black hole-like effects. Dark matter might also replicate the extreme conditions found near black holes. Black holes warp space-time so intensely that they create regions of extreme gravitational time dilation. Time slows dramatically near a black hole's event horizon, where the pull of gravity is so strong that not even light can escape. In theory, if dark matter could create similar localized distortions in space-time, it might allow us to manipulate the flow of time, slowing it down, speeding it up, or even reversing it. But how could we achieve this? Can we manipulate dark matter? Here lies the challenge. Dark matter is incredibly difficult to study, let alone manipulate. Scientists have theorized that dark matter might not be evenly distributed throughout the universe. Instead, it could exist in concentrated clumps or fields that remain undetected. If we could locate and harness these clumps, we might be able to create localized gravitational anomalies. Think of it like bending light through a lens, but on a cosmic scale, bending time and space itself. But this would require technology and understanding far beyond our current capabilities. Closed time-like curves, a time travel loop? Another fascinating concept in theoretical physics is the idea of closed time-like curves, or CTCs. These are loops in space-time that theoretically allow an object to travel back to its own past. Imagine a train track shaped like a loop that lets a train return to its starting point. CTCs are permitted by general relativity under certain extreme conditions, such as near-rotating black holes or in regions of intense space-time curvature. Could dark matter provide the energy densities or gravitational effects needed to create CTCs? If so, we might have a theoretical framework for backward time travel. The paradoxes of time travel. Even if dark matter enables time travel, it raises profound questions. What about causality, the principle that cause precedes effect? Time travel could lead to paradoxes, like the famous grandfather paradox. If you travel back in time and prevent your grandfather from meeting your grandmother, would you still exist? Physicists have proposed potential solutions to such paradoxes, including the idea of parallel timelines or multiverses. But these theories remain speculative. And let's not forget the potential risks of manipulating space-time. Could we destabilize the universe itself by creating wormholes or time loops? The implications are as vast as they are uncertain. What's next for time travel research? Despite the challenges, research into dark matter is advancing rapidly. Gravitational wave detectors like LIGO and Virgo are helping scientists study the effects of massive cosmic events, like black hole mergers, on spacetime. These observations could reveal new insights into how dark matter interacts with gravity. Meanwhile, advancements in quantum physics might one day allow us to directly detect and manipulate dark matter. Every breakthrough brings us closer to understanding its nature and its potential connection to time travel. Could dark matter unlock the mystery of time? The idea of using dark matter for time travel remains speculative. But history has shown us that today's science fiction often becomes tomorrow's science fact. By studying dark matter, we're not just exploring the invisible scaffolding of the universe. We're pushing the boundaries of what's possible. Who knows? Maybe one day we'll discover that the key to time travel has been hidden in the dark all along. What do you think? Could dark matter hold the answer to humanity's ultimate question? Let us know your thoughts in the comments below. And if you're as fascinated by the mysteries of the universe as we are, don't forget to like and subscribe for more cosmic explorations. Until next time, stay curious and keep exploring the unknown.